left figure is the actual figure. You have the device and there is current coming through the drain to the gate and goes out through the source. Okay. The impedance at the gate is ZG. ZG is the gate impedance, and Z is the source impedance connected to the source. So ZJ, these impedances can be combination of resistor, capacitor, and inductor. So all the three components may be there. Any of these components may be there. Any two can be there. Now the equivalent circuit of this we have seen in the last. Considering noise, we have seen the equivalent circuit to be the right hand side figure. If you look at the right hand side figure, the portion which is within the dashed box, that portion is for the device. So that portion models the device. The device is a voltage controlled current device. So the current is GM into VAGS. VGS is the voltage across the gate source capacitance, and to this device we are connecting two impedances ZG and ZDEG. ZDEG is between source and ground. Z between ground and gate. Now because of ZG, from ZG side, if you look into the device, the impedance between the gate and the source is ZGS. So ZGS gate source impedance. Similarly, the noise, only one factor we are considering, the noise, current noise is INDG. That is the current noise. INDG, we are considering that noise. Mean noise is INDG mean. That is in parallel with the device current. So there are two currents. One is the current device current, GMVGS, and the noise current, INDG. Both are from drain towards source. This is the circuit. Now if you consider this equivalent circuit, this is the small signal model. Small signal model for the device is this. Now for this small signal model for the device, we have to calculate or we have to find out the noise. Now the variance of this noise, by delta F is equal to variance of the noise due to ND. So ND noise variance by delta F whole into eta absolute square cross 2 times real part of C Z eta star ZGSW plus ZD square absolute of ZGSW square. So that is the noise. Now here on the variance of IND by delta F, that is equal to 4 times KT gamma ZDO. Last time we have discussed what are these components, what are these values. So this we have discussed last time. ZD also we discussed. ZD is equal to GM by ZDO root over of delta by 4 gamma. ZGSW is equal to omega CGS into ZGS. ZGS is equal to 1 upon SCGS in parallel with ZDEG plus ZG divided by 1 plus ZDEG. So these things you can calculate easily. You look at the circuit. From the circuit, you can easily calculate this. What is ZGS? That you can calculate because the capacitor is in parallel with ZDEG and the current source. So from that you can easily calculate this ZGS. Then eta is equal to 1 minus GM ZDEG by ZDEG plus ZG into ZGS. So all the parameters are known to us, and the equations for these parameters are now known to us. We can develop this small signal model. So this is basically the small signal model. What is the noise current that we have found out? The expression is above. Expression is used for the noise model. You are not required to derive these expressions, just remember these expressions. That is what is required. Now let us look at an example. Output current knowledge when Zs is equal to Rs. So in Zs there is no capacitance or inductance, and ZDEG is equal to 0. So the source is directly connected to ground without any impedance. First step is first determine the key noise parameters. What are the key noise parameters? First we have to determine that. So for a 0.18 micron CMOS device, we will assume this following. C is equal to minus J 0.55. That is what is small c. Gamma is equal to 3. For a 0.18 micron device, gamma is equal to 3. Delta is equal to 2 gamma is equal to 6. Because gamma is equal to 3, so delta is equal to 2 gamma, that will be 6. GM by GDO, that ratio is equal to half. So that ratio is equal to half, that gives us ZD is equal to 0.32. We have seen the expression for ZD. Expression for ZD is GM by GDO root over of gamma by 5. So put all those values, you will get this. Then in this second step, calculate what is eta and ZGSW. Take eta to be equal to 1. For a 0.18 micron CMOS, eta is equal to 1. So then what is left is ZGSW. ZGSW is equal to omega CGS into Rs in parallel with 1 by J omega CGS. So that if you simplify, that is omega CGS Rs divided by 1 plus J omega CGS into Rs. This is simple algebra you can do. Just parallel connection, 1 by R1 plus 1 by R2 is equal to R1 plus R2 by R1 R2. So R is equal to R1 R2 divided by R1 plus R2. That is applied here. That principle is applied here to find this out. So these are the two steps. Then the third step is plug this value into the derived expression for the noise figure. So the covariance of NDG current divided by delta F, which is equal to covariance of ND current divided by delta F into drain noise multiplying factor. The drain noise multiplying factor is equal to 1 plus 2 times real part of minus J absolute of C ZD JGSW plus ZD square ZGSW square, absolute square. ZGSW expression we know when omega is much less than 1 upon Rs into CGS. In that case, ZGSW will be approximately omega into CGS Rs, because in the denominator omega CGS Rs is much less than 1. So in the denominator the second term can be neglected, neglecting that in the numerator term. So using these values you will get the covariance of NDG current divided by delta F to be equal to covariance of ND current divided by delta F whole into 1 plus ZD square into omega CGS Rs square, which means that is the gate noise contribution. This part is second part, ZD square omega CGF RS whole square, that is gate noise contribution. So starting with drain noise multiplying factor, we only reach at the gate noise contribution only. So the contribution to noise is coming from gate. We under the approximation that omega is much less than 1 upon RS into CGS. Now this figure shows you, this plot shows the drain noise multiplying factor for a 0.18 NMOS device. Now if you look at the top of this figure, this is like a S, inverted S. If you look at the S, invert the S, this figure is something like that. So it starts at a high value, drain noise gain factor is 1, so it starts there, then gradually it drops, it follows this curve and drops to 0.75. So at when the normalized frequency is below 1/10, it remains almost 1. So on that condition, when it remains below 1/10, which means frequency F or omega is much less than 1/RS into CGS, because it is below 1/10. When it is above 10, so it is greater than, omega is greater than RS into CGS, drain noise factor comes down to 0.75, and in between them it follows an inverted S path. So from this we can conclude that gate noise has little effect on common source amplifier when source impedance is purely resistive. Now with once we are equipped with our knowledge on noise and modeling of small signal device, then we can use those noise to broadband amplifier design considering the noise. So broadband amplifier design considerations for noise, let us consider this. Now look at this figure. This figure we have already seen earlier, the same figure. So on the x-axis is the frequency. If it is, when the frequency is less than or when omega is less than 1/RS CGS, this part is towards the left of the red mark portion, and towards the right it is greater than that. At the red mark portion it is equal. Now we also have seen that 1/F noise corner frequency, at that frequency the drain 1/F noise is equal to 4 kT gamma GDO, and the line 4 kT gamma GDO is the thermal noise, drain thermal noise is that. So drain thermal noise is the chief issue of concern when designing the amplifier with more than 1 GHz bandwidth. 1/F noise corner is usually less than 1 MHz because frequency is small. Gate noise contribution only has influence at high frequencies when omega is greater than 1/RS into CGS or F is greater than 1/2πRS into CGS. Noise performance specifications is usually given in terms of input referred voltage noise. Now where it is given? It is given in the specification sheet or data sheet of the device that we are going to use. If you are designing an amplifier, you have to purchase, one has to procure or purchase a device, a CMOS device. So CMOS transistor you have to purchase. When you purchase CMOS transistor, with the transistor its specification sheet or the data sheet will come within the transistor. So that sheet will mention the noise performance specifications. Now, if you are going for narrowband amplifier noise requirements, then the required region will be very narrow. So here in the figure you can see the frequency range over which we are designing the amplifier. The frequency range, this gray area, that is very narrow, compared to very narrow band of frequency. So over that band of frequency, there is the noise contribution is mostly the thermal noise. Other noise are not there, and that noise is limited to 4 kT gamma GTO over that range. So what we do here is we focus on the narrowband operation. We don't care about noise outside this band, which means 1 by F noise corner frequency is of no use, or gate noise contributions, those are also of no use. So it will be filtered out automatically because the amplifier is operating over a small band. Gate noise is a significant issue here. Using reactive elements in this source, if you connect a reactive element to the source, then that will dramatically impact the influence of gate noise, because that stores the energy. So noise will be stored, the noise generated at the gate, some amount of noise will be stored there. Specifications usually give in terms of noise figure, and so what is the noise figure, that will be given in the specification, device specification. So now let us consider the impact of gate noise. With ZS or source impedance is equal to RS plus SLG. So you can see the figure here. In the figure, there is a dashed line. On the two sides of the dashed line, towards the left side is the source, towards the right side is the amplifier or the device. The amplifier equivalent circuit is within the dashed box. That we need not discuss anymore about the circuit, equivalent circuit. Look at the left side. In the resistor, in the source, we have V in, then the source resistance. Because there is a source resistance, it will get heated up as we discussed earlier. Because of that, we will get is noise, thermal noise. So ENS is the thermal noise, that is, so that much of current, that is the additional current due to the source resistance. And with the source resistance, there will be an inductance. Inductance is not connected. Source resistor, when you consider a inductor, it will come inherently there is a resistance in the inductor. Similarly, with resistor, there will be an inherently there will be an inductor. So this is that inductor. So inductor is LG. So when we are going to analyze this, the first step is determine the key noise parameters. Always the first step is determine the key noise parameters. For 0.18 micron CMOS, again assume this values. C is equal to minus J 0.55, gamma is equal to 3, delta is equal to 2, gamma is equal to 6, GM by GDO is equal to half, which gives ZD is equal to 0.3. Step 2 is take eta is equal to 1, then calculate ZGSW. ZGSW expression we know, so this is the expression for ZGSW. Just so simply, here what we have done is, instead of only RS, with the RS we have, instead of RS we are using ZS. ZS is equal to RS plus J omega L. So that much is the difference. So instead of RS omega CGS into RS for RS, now we are replacing that with ZS. So ZS is equal to RS plus J omega L. In the denominator also we have doing that. Then set LG find out what is LG such that it resonates with CGS at the center frequency omega 0 or the frequency at which we want to operate the amplifier. It's a narrowband amplifier. So set LG such that it resonates at CGS at center frequency omega 0 of the narrowband of interest, which means 1 upon root over of LG into CGS is equal to omega 0. So and then we know what is Q factor. Q is equal to 1 by omega 0 into CGS into RS, or that is omega 0 LG by RS. These are the normal expressions for Q. Now calculate Z GSW at omega 0. So in the expression for Z GSW for omega, put omega 0. So put omega 0, then that will be equal to omega 0 CGS into Q square RS minus J root over of LG by CGS. That will be equal to Q minus J. Just plug in the value of Q and multiply omega 0 CGS everywhere. So first term will be Q square into omega 0 into CGS into RS. Now omega 0 CGS into RS is 1 by Q. So Q square by Q, that will be Q. The second term is omega 0 into CGS into root over of LG by GS. Now root over of LG by CGS into CGS is equal to root over of LG. Root over of LG into CGS. Root over of LG into CGS is root over of omega 0. So omega 0 divided by root over of root over of LG into CGS is equal to 1 by omega 0. So omega 0 into 1 by omega 0 is 1. So the second term will be minus J. So ZGSW is equal to Q minus J. Now we already know what is the expression for the noise expression. Now in that substitute for ZGSW Q minus J. So putting those values, you will get 2 times real part of minus J into absolute of C into xi d into JGSW. Now put the value that we have found out for JGSW. Put in that value, we will get this will be equal to minus 2 times C absolute into xi d. Similarly, xi d square into ZGSW square or ZGSW absolute square, that will be again equal to xi d square into Q square plus 1. Using those values, the noise expression will be a variance of ND current by delta F into 1 minus 2 C absolute C xi d plus xi d square into Q square plus 1. So this is this second part, except the constant in the bracket, except the constant 1. The rest part is the gate noise contribution. So gate noise contribution is a function of Q now. So this will rise now. If you look at this will rise or this will increase monotonically with Q, which means as you increase Q, the gate noise contribution will increase. Now look at this figure. This figure explains that at what value of Q the gate noise will exceed the drain noise. The expression is for that. Now gate noise is the red line shows you the gate noise contribution. The black line shows you the drain or thermal noise contribution, which is at 4 kT gamma GTO. Now as you keep on increasing Q square, you will reach a frequency. As you increase Q square, then you will reach a value of Q for which this total noise will be then thermal noise, so gate noise will increase there. So to determine the crossover point for Q value, first take this value, the variance of NDG current by delta F is equal to the expression we know, we have found out the expression variance of ND current by delta F into 1 minus 2 absolute of C into ZD plus ZD square into Q square plus 1. So that will be equal to the variance of ND current divided by delta into 1. The term in the bracket should be equal to 1. Under the when the term within the bracket it becomes equal to 1, that is the point, or that is the crossover point. So that will be 1 when Q is equal to square root of 1 by ZD square minus 1 plus 2 times absolute C by ZD, which is equal to 3.5 for a 0.18 micron device. So critical Q value for crossover is primarily set by the process means design process or manufacturing process. Now let us calculate the signal spectrum at the output. So calculation of the signal spectrum at the output of the amplifier. Same circuit with the equivalent circuit. Now we are taking it the same circuit. First what we will do is we will calculate the relationship between V in and I output. Input voltage and the output current. Find out the relationship between these two. So I output for the signal is equal to GM into Vs. Now GM into Vs is equal to GM into, for Vs we can write 1 by V in divided by 1 minus omega square Lg into Cg plus j omega Rs into Cgs. Because Vgs is equal to V in by Z in. So Z in we know, Z in expression is given below. At resonance, omega is equal to omega 0 and there will be no reaction part, reactive part. So putting those things, I out signal is equal to GM VGS, that will be GM into V in by j omega 0 Rs into Cg. So that will be equal to GM into minus JQ into V in. So spectral sensitivity based on this, the spectral sensitivity means the sensitivity to the frequency. So once we know what is the current at the resonant frequency, if you deviate from resonant frequency, how much it will affect the current, that is what is spectral sensitivity. So spectral density of the signal at the output at resonant frequency is S, capital S is the spectral density. S I out of the signal at F is equal to GM minus JQ absolute square into S in F. So that is GMQ square into S in F. S in is the spectral density of the input signal. Now consider what is the impact of Q on the signal to noise ratio. SNR means signal to noise ratio. We are ignoring the RS noise due to RS. So source noise we are ignoring. Look at this figure. The only additional part here is the Q square in blue, which is the signal spectrum. So the signal spectrum is above 4k T gamma GTO, but below the top value which can be 1 to whatever it is. So SNR, assuming constant spectrum, ignore the noise from arrays. So SNR output is equal to SNR I out signal frequency divided by SNR I out due to noise. That is what is signal SNR output. So this is the spectral density due to output spectral density of the output current divided by spectral density at the output noise. That ratio, which is approximately equal to spectral density at the output current. We have found the expression, that is GMQ whole square into spectral density of the input signal divided by spectral density of the output noise is the spectral density is the covariance of the NDG current by delta F. Now from this we can say for small q, so that gate noise is less than drain noise. When we have small q, gate noise will be less than drain noise. So under that condition, SNR output improves dramatically as q is increased. When the gate noise is greater than the noise drain noise, SNR output improves very little as q is increased. Now let us take some definitions. One is noise factor, second is noise figure. Noise factor is defined as F. Noise factor is defined as F, which is equal to SNR at the input or signal to noise ratio at the input divided by signal to noise ratio at the output. Or you can say noise factor is the ratio of the signal to noise ratio at input and signal to noise ratio at output. Similarly, noise figure is equal to 10 times log of the noise factor. That is what is noise figure. These are the definitions. Now to calculate SNR input and SNR output, or to find out noise factor, you require SNR input and SNR output. So to calculate that, SNR input is equal to absolute of alpha square V in square divided by so SNR input is equal to absolute alpha square into V in square divided by absolute alpha square into variance of 10 arrays E square, which is the error. So that is equal to V in square divided by variance of E in RS, where alpha is equal to Z in by RS plus Z in. Similarly, SNR output is equal to absolute alpha square into capital GM square into V capital GM capital G subscript M square absolute of that square into V in square divided by absolute alpha square into absolute GM square into variance of E and RS plus a variance of I in out or variance of N out current. Now GM in this expression, GM is equal to I out by. Now you can see what is the Vx. For Vx is the voltage across the linear time invariant circuit, which is assumed to be noiseless. Look at the figure. In the figure, the dotted box, within the dotted box there is a box which is the LTI circuit, which is noiseless. The noise is there, the current noise is I out, which is connected on the right hand side that you can see. Then we have, after that there is the ZL or the load impedance through which the current is I out. Similarly, if you look from the output side, from the load side to the circuit, then the output impedance is Z out. If you look from the source side to the circuit, the input impedance is Z in. V in is the source voltage, RS is the source resistance, and the noise due to resistance is En due to RS. So En RS is the noise due to resistance. Now let us calculate the noise factor. The first part of calculating the noise factor, same circuit with RS, we are adding LG. First what we will do is we will calculate SNR output, which must include RS noise for the circuit. So we have to have the noise. RS noise calculation is same as that for V in. So I output RS is equal to GM into minus JQ into mean of E noise, so ENS. So that will give us the spectral density of the output current in the presence of the source resistance is equal to GM into Q whole square, that into 4 KT into RS. So SNR output is equal to, from that you can say SNR out is equal to GM into Q whole square into input spectral density divided by variance due to NDG current divided by delta F plus GM into Q whole square into 4 KT RS. So on that you get as SNR output by using the definition of SNR output. Then calculate the SNR input. SNR input is equal to spectral density, input spectral density divided by the variance of noise source, variance of the noise at the source divided by delta F, that is equal to the spectral density at the input divided by 4 KT RS. Now we have seen the expressions for SNR output and SNR input. So noise factor will be SNR input by SNR output. Just divide these two expressions. That will give us the noise factor as 1 plus variance of NDG current by delta F divided by GM into Q whole square into 4kT RS. That is the noise factor. Now once we know noise factor F, then you can find out what is the now from the previous analysis we also know what is the variance of the NDG current by delta F, that is equal to 4kT gamma ZDO into 1 minus 2 times absolute of C ZD plus Q square plus 1 whole into ZD square. So that we know. There from that we use this using this final expression for noise factor is equal to 1 plus gamma ZDO whole into 1 minus 2 times gamma absolute of C into ZD plus Q square plus 1 into ZD square divided by Gm into Q whole square into RS. This is the expression for noise factor. So we have found the expression for noise factor. Then I will try to modify the denominator using the expression for Q and omega T. Q you know is equal to 1 by omega 0 into RS into CGS. Omega T is approximately equal to Gm by CGS. These two we know. So since we know these two, now let us rewrite the denominator. Gm into Q square into RS is equal to Gm square into Q into RS. So this will be Gm square into Q into RS by omega 0 RS into CGS into S. Now CGS. So from where do we get this? The denominator, because Q is equal to 1 by omega square RS CGS. So for 1 Q, Q square is equal to Q into Q, that is equal to Q into or Q by omega 0 RS CGS. That is what we are using here. So that we can write as Gm into Q into Gm by CGS into 1 by omega 0. So that because that comes from omega T expression is Gm by CGS. So use that. So that will give us Gm into Q into omega T by omega 0, or using this Gm by CGS as omega T, that is this. So resulting expression for the noise factor now is 1 plus omega 0 by omega T into gamma into dGO by Gm whole of that into 1 by Q whole into 1 minus 2 absolute of C into ZD plus Q square plus 1 into ZD square divide that is the, and that part is called the noise factor scaling coefficient. This coefficient is called the noise factor scaling coefficient. Noise factor, from this you can say that primarily depends on two factors. One is the Q factor, other is omega 0 by omega T, and definitely process specifications. So this is the expression for the noise factor. Now what will the minimum value of this? Minimum noise factor. When we will get minimum noise factor? What will the minimum values of this? So we see that from this the noise factor will be minimized for some value of Q. So if you keep on increasing Q, noise factor goes on to decrease, or it goes on to increase. So there is a part which decreases and there is another part in which it increases. So we do this analytically by differentiating with respect to Q and solving the peak value. That is only where the derivative is equal to 0. Differentiate the noise factor with respect to Q, then equate the derivative to equal to 0, find out what is the value of Q. So if you look at the term list book that is prescribed, the minimum noise factor for the MOS common source amplifier without any degeneration is found to be 1 plus omega 0 by omega T into 2 by root 5 into root over of gamma delta into 1 minus absolute C square. This is called the noise factor scaling coefficient. This plot shows you the minimum noise factor and noise factor versus Q. This is the noise factor versus Q curves. You can see when C is equal to minus J0, when C is equal to minus J0.55, when C is equal to minus J1. So as C increases, the minimum value dips. The noise factor also dips. So noise factor scaling coefficient dips down, goes down, it decreases as C increases. That you can see. So this is achievable values as a function of Q under the constraint that omega 0 is equal to 1 upon root over of Lg into Cg. This is the main part. Now you can see when C is equal to J0, the blue dashed line, so the minimum point approaches that dashed line. Similarly, for J, C is equal to minus J 0.55, the minimum value approaches the red dashed line. So those portions or those noise curves, they will meet if you approximate Q square plus 1 is equal to Q square, which means Q square is very large compared to 1, it is much larger than 1, then they will meet. The minimum across all values of Q is between these 2 points, 3 to 4. Between 3 to 4, the minimum value is there. And Cj is equal to minus J1, that gives you 0. Minimum will be 0. So that is along the x-axis. So to achieve the minimum noise factor, what we require for common source amplifier without degeneration, minimum noise factor can only be achieved at resonance if gate noise is uncorrelated to drain noise. That is if C is equal to 0. That we'll see later. We typically must operate slightly away from the resonance in practice when you are using the amplifier to achieve minimum noise factor, since C is never going to be 0. So since C is non-zero, always we practice slightly away from the resonance. Then the question is, how do you determine the optimum source impedance to minimize the noise trigger in classical analysis? And that is a question that we require to answer. Just read the book and tell me the answer. That is your homework. With that, we come to the end of today's discussion. We will have your exam sometimes in this week. Since we are going to have your mid-sem exam, let us decide that we will have questions from the first unit only. So I will set your question and from the first unit only. Prepare the first